Okay, so the multi-grid, the idea is, let me try to do most of the conversion on the coarse grid as to be doing on the fine grid. Okay, the prerequisite of being able to perform the work on the coarse grid is for the sufficient smoothness, right? And in particular, what I want to be solving on the coarse grid is the error equation. So let's actually start to review the error equation. So basically, we're trying to solve AU equal to B. But now we have an AU that is not equal to B. We have an A of UK, okay, equal to B, but not exactly equal to B. It's equal to B minus a residual RK. So RK being equal to A times UK minus B, or in this case, B minus A times UK, is basically how much the equation is not satisfied. Okay, and if we can solve the error equation, which is A times EK equal to RK, then we can correct the solution. We know the true solution. The true solution is U would be equal to UK plus EK, right? That's because A times UK plus EK would be equal to AUK plus AEK, and AUK we know is B minus RK, and AEK would be just the RK, so that's equal to B. So basically, if we can solve the error equation, we can correct the non-converged solution and get the true solution. So basically, multi-grid is trying to solve the error equation in a coarse grid, and the requirement is for the solution error as well as the residual to be smooth, so that we can interpolate the residual, okay, into a coarse grid, and then interpolate back the solution of the error equation, which is the solution error, back to the final grid. All right, is there questions? Right, so the procedure is to, in a fine grid, first step is on the fine grid, smooth the solution. And when we say smooth the solution, we actually mean by smooth the solution error and the residual. How do we do that? We do that by performing a few iterations, Jacobi iterations. And then, when the residual is already smooth, interpolate the residual RK to a coarse grid. And the third step is to solve the error equation, A times EK equal to RK on the coarse grid. And the fourth step is to interpolate the solution EK back to fine grid, and my UK plus 1 is going to be UK plus EK, right? We correct the solution. So let's go through the code we wrote last time to figure out what's wrong. So let's do this, iterate, and so this is the code we wrote last time. First of all, we wrote a code for computing the Laplacian, right? So this code is basically taking a field x well, we actually call, let's actually call it U. So we called it U, and the Laplacian of U, it's set to 0 first, and basically we are taking the finite difference operator, second derivative in x, plus the second derivative in y, right? So that's returned as a Laplacian of U. All right. So that's basically calling this function is equivalent of multiplying a solution with our matrix A times U. Okay. And then we wrote our code for the Jacobi iteration. So the Jacobi iteration also takes a solution, let's say UK, and returns UK plus 1. So first of all, it computes the size of the array in order to compute dx and dy, and then it says my UK plus 1 equal to UK plus is equal to UK just on the boundaries, right? So basically this is just a set in the boundaries. And since in our case our boundaries are set to 0, we don't even need this. We don't even need this line. We can basically set UK plus 1 equal to all zeros. And then UK plus 1 is equal to basically using the Jacobi formula. It is equal to D inverse times B minus off diagonal times UK. And here the D inverse is basically a division by the off-diagonal entries of the matrix, because D is a diagonal matrix, right? So in the parentheses we have B minus basically the off-diagonal parts of the Laplacian. It's the same as the x and y second order derivatives, except for the minus U part, minus 2U part, right? So the Laplacian would be U of I plus 1j plus U of I minus 1j, then minus 2 times Uij. I mean, the minus part is diagonal, which is moved to the diagonal part. Okay, so now that's our Jacobi iteration. And if we perform Jacobi iteration on the system, we can see how fast it converges, right? So so last time we tried to import the whole image, and basically we get 4095 by 4095 by 3 integer. So we can set our U exact to be that image. So let's first set it to zeros, 4097. So that basically includes the boundary. I mean, this image didn't include the boundary. Now we include the boundary, and we set U exact the interior 2 to n minus 1, 2 to n minus 1. That's the interior of this array, to be double of F35 first, and we are dividing that by 127, which is the maximum value of unsigned integer 8 bits. Okay. So if I have in binary, if I have 8 bits of 1, that is exactly 127. All right. So that's the maximum possible value of this array. Okay. So if I do this, I am sure U exact. What you see is this image being my exact solution. So if this is my exact solution, I can evaluate my right-hand side to be just the A times the exact solution. And here, the Laplacian is my matrix A. Exact. All right. So now I computed my B to be a double array of the same size. So now let's try to solve this equation by Jacobi iteration. So if I set U equal to zeros, 4097, so that's our initial guess, and U equal to Jacobi U and B. So that's calling our Jacobi iteration. We can do this again, and you can see like each one takes actually non-negligible time to complete, right? Because the we really have 16 million grid points in this case. If I do this several times and we look at how the solution look like, it's still totally black, right? So basically Jacobi iteration converges too slowly for a grid of this size.